So, very good afternoon to everyone. I'm Dr. Pratibha Jadhav. I warmly welcome you back to the second session of Parivartan on the behalf of Plastindia International University. So, to commence today's session, I would now like to invite Dr. Prashant Gupta to introduce about the Plastindia International University. Over to you, sir.
Thank you. Yeah, I hope the screen is visible.
Yes, sir. Yeah,
Okay,
screen is visible.
great,
Yes.
great. Yeah, so my name is Dr. Prashant Gupta. I'm associated with Plastindia International University as a senior assistant professor, and I'm more than grateful to take you through what Plastindia International University is all about. Right. So our vision is to develop world-class university in plastics technology, research, and innovation. As you can see here, we are located in the city of Vapi in the state of Gujarat, and it's very near to the financial capital, as we know, of our country, which is Mumbai. So we are situated at a very close distance from Mumbai, and the reason why we are situated here is very important, especially when we keep in mind the industry. So we are situated in a plastic cluster. We are talking about a belt of processors in and around Vapi, which is Daman, Silvassa, Umargaon till Valsad. You'll find there is a belt of plastic processors, the maximum that are concentrated in our country. We have a very important academic partnership with UMass Lowell, which is University of Massachusetts Lowell. They have a campus in Boston, and they have been offering this plastics education since 1954. So we'll take you through what our university is about. We'll talk about your parent body, which is Plast India Foundation. So Plast India Foundation is an apex body of plastics which have come into existence due to all the industries joining hand. So we have been found by a host of organizations which are taking care of a lot of policy making and decision making into polymers. We're talking about IPMA, we're talking about CIPED, OPPI, Lex Council, IPI, GSPMA, Indian Plastic Federation, and we have some constituent and associate members as well. So Plastic India Foundation came in the early 1980s into existence, and they had an aim of helping the country grow in terms of plastics, and that is how we have come into existence, which is Plastindia International University. So we are very proud to say that we are a not-for-profit organization. We are founded by the plastic industry for the plastic industry. So more about the UMass Lowell and PIU partnership. So we have entered into a service agreement with UMass Lowell, where they help us, or they share their technical know-how with us in terms of designing of the curriculum. So the curriculum that we cover in India is a majority consisting of what they cover in the US. So subjects which are taken from there are being taught here. We have student and faculty exchange programs to run with them, applied research and community-based projects, opportunities for engaging students and researchers, for establishing peer relationships and mentoring opportunities. We have faculty development program with them for wherein we send our faculties to UMass Lowell for training and helping our students to learn at an international level, and also to conduct webinar series in technical polymeric domains. So UMass Lowell, the institute which is having plastics in their curriculum, it is a 70-year-old curriculum that they are covering, which started back in the year 1954. So why PIU? So there is an exclusive focus on plastics and polymer engineering. So there are a few universities in India which offers these, either government or private, but you would find more of institutes offering these kind of programs. Now we are one of our kind where we offer customized courses on focusing on polymers. So that is where we are different from what is existing. We have an industry driven education. So we are talking about state of the art machinery. We are talking about hands on training. So the instrumentation and the machinery, largely processing and others that we are going to bring in, or that we have at this point in time, are at par in level with what is used in the industrial, manufacturing level. We have a strong industry integration, and we help students on hands-on learning. Another very important thing is 100% placement guarantee. We'll talk more about it going forward. We offer scholarships and financial aids to students who have secured good merit and who need it from a financial level. And you must and PIU, the degree that you do at PIU becomes a gateway to global education and excellence, especially when we are talking about going for a global immersion program at UMass Lowell, or maybe going for higher education there. Now let's talk about scholarships and placements. We have merit-based scholarships wherein students get a tuition fee waiver, a certain percentage depending on what marks they have secured in going courses. That if you are trying to get into the first year, we are talking about 12th, and we are trying to get into the second year, we are talking about diploma. If you have need-based financial aid, we provide that. There is a lot of industry sponsored education where people stalwarts from the industry, they come forward and sponsor education that we give away to our students. And of course, as PIU is AICTE and UGC approved, we also offer government scholarships, whatever schemes are running. So there is a high return on investment. So the cost of education at PIU is very, very minimal. So graduates secure high paying job, which is, pretty much in the first year itself, you take away all the money that you have invested, maybe double of that, if not less. And as we offer 100% guaranteed placements, and students can go up to a package of 6 to 7 lakhs average. It's worth investing into a course like this. And we also say that if a student has a particular marks like 6.5 CGPA, and the barrier that we are keeping of 6.5 is very simple, because when we are saying that we guarantee placements with a certain package, the student should if a student doesn't score a particular marks, and if the company says that we will not allow you to sit for our exams, the campus placement exams, then it becomes difficult. And that is why we encourage our students to secure 6.5 CGPA and above, so that it becomes easy to give them the package that we promise. So that is our refund policy. If you are above 6.5 CGPA and we don't give you placement, you would find that we will return all 4 years fees to you. So these are global faculty, industry experts, and mentors. So you can see on the left side of the screen, we have a lot of industry global experts, and which are basically the departmental faculties from UMass Lowell, and we have our own industry experts as well, ex-Reliance, and these are big people in the industry. This is our faculty team. So just a general, note that every faculty that is serving here has a doctorate and a degree from a very reputed institutions like ICT, IITs, and NITs. The courses that are offered are two, that is plastics and polymer engineering. We offer the first year entry after 12th with physics, chemistry, and mathematics. And there is a direct second year entry as well, which is being offered to any diploma students who want to come into plastic. Let's say if there is a mechanical student and is eager to learn plastics, we welcome those students as well. And we have a BTech in computer science and engineering, for which this year we are only offering a first year course. So the companies that you see in front of you are our companies which have agreed to hire from our campus as soon as the first batch goes away. This is a general description of fees. The fees that we took last year was 75,000, which is decided by there is an FRA, fees regulating authority, government of Gujarat, and this might change by 10% this year, and this is payable per semester. And there is a security deposit of 10,000 rupees along with a library deposit of 2,500, which is payable once, and it is refundable in nature, that you need to pay before the first semester. So this is the building that we have at this point in time. We'll see some images that will help you understand. So we are just situated 500 meters away from the bullet train station of Vapi. This is a 33-acre campus that you see. So this is our main gate. This is the main building of School of Engineering. These are some of the laboratories, engineering, chemistry. So there you can see the students performing the practicals. These are first year students who were enrolled in engineering chemistry course. This is a physics laboratory, a computer state, 60 students at once. This is the engineering graphics laboratory, design thinking. So we have exposed our students in the first year itself to a subject known as design thinking and innovation, which deals with 3D printing right at the first stage of the students. This is an engineering workshop where they get exposure to all the metalworking based machinery and even CNC machines and processing equipments as well. This is professional communication. So in the first and the second semester, we tutor students in English, which is professional communication. The idea is to make them ready to, go to UMass Lovell in the last semester if they feel like they want to go. This is the library and the reading facilities. This is the classroom. The whole building is centralized AC, canteen area, so boys or girls common rooms. So there are individual common rooms for both boys and girls, and there are recreational facilities as well. This is the plan which is going to get executed in the near future, wherein you can see there are buildings that are coming up, wherein we'll have an MBA based school, and then there would be an auditorium. There will be a school of continuing education, and there will be a one of its kind school of sustainability. So this phase 2 and 3 are slated to grow in the next 5 or 7 years in our future. So thank you. Thank you for the time and patience to hear about what Plastindia International University is all about. So back to you, Pratibha madam.
Yeah, thank you, Dr. Gupta, for sharing an insightful overview of Plastindia International University. So let us begin the session. So very quick, I will brief about the session. So today's session is focused on the transformative role of nanotechnology in modern science. So this talk delves into the self-assembly and biocompatibility of the nanomaterials. So it touches on scalable and sustainable manufacturing techniques and its real-world applications and emerging trends will be showcased. So the lecture also includes the future prospects and applications of these nanomaterials. So it is my privilege to introduce our speaker, Dr. Aniruddha Chatterjee. So, Dr. Chatterjee currently working as an associate professor in the Department of Plastics and Polymer Engineering, School of Engineering, PIU. So Dr. Chatterjee brings with him over 21 years of extensive experience in teaching, research, and industry with a specialization in polymer science and engineering and nanoscience and technology. His career includes prestigious recognitions such as the DST Young Scientist Postdoctoral Fellowship, CSIR Senior Research Fellowship, and UGC Project Fellowship. Also, he has held key academic positions, including Head Department of MIT Chhatrapati Sambhajinagar, Dean R&D and Innovation, and governing body member. Dr. Chatterjee's research contributions are remarkable. Till the date, he has 47 publications in reputed international journals. Among all, 5 granted patents, 19 book chapters, and numerous conference presentations as well. So his work spans critical areas such as polymer blends and composites, hybrid nanostructures, nanocatalysts in green chemistry, nanoadsorbents, and biopolymer nanocomposites. Uh, with successful completion of 5 major research projects worth rupees 123 lakh and active mentorship of PhD and MTech students, he continues to make a significant impact on the scientific community. So, with this, I would like to invite our today's speaker, Dr. Aniruddha Chatterjee. Over to you, sir. Yes, sir, it is fine.
Okay, okay. So thank you, Pratibha, for your brief introduction. So hello, everyone. I am Dr. Aniruddha Chatterjee, working as a associate professor in Plastindia International University. So I welcome you all for today's session. That is on nanotechnology revolution, the magic of polymeric nanostructures under Parivartan, a webinar series on advancements in polymers and sustainability. So nanotechnology is the most advanced and rapidly growing technology in the last 50 years of technological development or advancement. So that's why sometimes it is called most fascinating field in 21st century actually. So as an interdisciplinary technology, so this nanotechnology actually breaks the barrier across all fields due to the unique characteristics of its extremely small particle size, typically less than 100 nanometers. So basically, the reduction of size, enhanced surface area, then quantum effects, and also altered chemical reactivity of nanomaterials in a smaller size. So these above techniques basically, you can say, these qualities, unique qualities or unique characteristics enable innovations in various fields such as medicine, electronics, energy, agriculture, then in environmental science, in material science, and other fields also. So due to its unique characteristics and you can say smaller size below you can say 100 nanometers. So it is widely accepted technology by young researchers for conducting advanced research in nanotechnology across almost all fields. So now what is nanotechnology? So nanotechnology is the field of science and engineering that deals with manipulating matters at a smaller scale or in nanoscale, which is roughly between 1 to 100 nanometers in size. And this involves designing, producing and using structures, devices and systems by manipulating atoms and molecules at lower level. And sometimes it is compared with human hair, which is about 8,000 nanometer in width. So you can see here the human hair fragment, and in the background section it is the single or carbon nanotube. You can see the difference in between the size of these nanostructures or single wall nanotubes with human hair. And here is also the silver nanowires. This is the round, so this is the silver nanowires. It is resting on human hair. So you can say in simple terms that nanotechnology is defined as the engineering at a very small scale. We are doing we are changing the size, changing we are incorporating different types of nanomaterials, and whatever that one is in very smaller scale. So that's why it is engineering at a very small scale. So what are the importance of nanotechnology? So you can see, so as I already said, that it is interdisciplinary technology. Now nanotechnology in today's time, it is in everywhere. You can see, so it is right from food and agriculture to mechanical engineering and robotics, in medicine, then in construction, then advanced materials and textiles, information technology, biotechnology, aerospace, and also in defense sectors. So then what are the features of nanotechnology? So it enables manipulation of matters at the atomic and macromolecular levels, and it also creates materials with unique and enhanced physical and chemical properties. Then nanofabrication leading to a faster and more efficient devices. You can produce you can say more faster and efficient devices with the help of nanofabrications. Then opens new possibilities in science, engineering and innovation. So with the help of nanotechnology, you can make new materials in different fields. Mostly nanotechnology is mostly used in medicine, actually medicine and medical sector. So many innovations already done in that particular field, and also in agriculture and mechanical engineering sections. Then supports sustainable and eco-friendly technologies, and also this accelerates the space of technological and advancement across different sectors. So So this is about the history of nanotechnology. So the concept of nanotechnology was first presented by Richard Feynman, the professor of California Institute of Technology, during one of his lecture in 1959 in American Chemical Society. So the famous lecture was on "There's plenty of rooms at the bottom." So it means that whenever you are reducing the size, you will get more area, more surface area to work actually. So, and that particular word nanotechnology was first introduced for the first time to the scientific world by the professor of Tokyo University and Science, that is Professor Norio Taniguchi, in the International Conference on Industrial Production in Tokyo in 1974. So it was first, the concept was first presented by Richard Feynman and was first introduced by, and the terminology nanotechnology was first introduced by Professor Taniguchi in 1974. And in 1980s, Dr. K. Erk Drexler, he developed and popularized this concept of nanotechnology, and founded the field of molecular nanotechnology. So, and this is he is the first person to get a doctoral degree in molecular nanotechnology in 1991. So this is about the history, small history of nanotechnology. Now, Indian research publication in terms of nanotechnology. So, over the last 3 decades, you can say India has demonstrated significant growth in nanotechnology research publication. So, in 1990, with only 10 publications in nanotechnology field. In 2009, it was increased up to 532 folds actually over 20 years. So almost 5,319 publications published in 2009. And in 2013, India ranked the third globally in the number of nanoscience paper published, only after China and USA. So this is the latest scenario in 2023. So total publication is 26,792 in Web of Science database, in terms of Web of Science database. Then Indian global ranking is second, and in terms of total number of publications in nanotechnology field. Then publications in Q1 journals is almost 9,236 in top quartile journals, securing the third position worldwide in this particular category. Then almost you can say publications in top 10% journals with 3,134 articles published in the top 10% of journals. India ranked fourth globally. And local share in nanoscience, approximately 15.77% of India's total scientific publications were related to nanotechnology, indicating it that a significant focus on this particular field actually. So what is nano actually? What is nano? So a nano means it's a very tiny particle. It is basically, this nano word is basically coming from Greek word that is very small, or you can say it's a tiny particle. So if you see over here, that is Jeddah Tower, Saudi Arabia, and it is under construction, and it will complete it by 2030. And this is the tallest, you can say, building in this world. It will be the tallest building in the world, and the total length, or you can say the height of this building is more than 1 kilometer, means 1,000 meters. Now, this is about the figure of one child, maximum of 1 meter of height, and this is about ant is 1 mm maximum length, you can say 1 mm. And here is the bacteria is maximum length of 1 micron, and a DNA molecules is approximately 2.5 nanometer in size, average size. So you can say compare 1 nanometer is equals to 10 raised to minus 9 meter. So you can say almost 1 billionth of a meter, you can say. So this is the length scale of nanometer. Here you can see that from J-Dono nanowires to single wall carbon nanoparticles, they are under the nanometer scale. So you can say that as the particle size decrease, you can say a smaller size of different materials. So now what is nano? So why nano? Why we are using nanomaterials? So what is the reason that maximum researchers or young researchers or today's researchers, they are doing extensive research in nanotechnology field? So the reason behind that, actually large particle properties are constant with respect to size, but as we reducing the size, then at a certain size, nanomaterials are having size dependent physical and chemical and other properties. So you can say it is basically a size dependent technology. So depending on the size, the physical and chemical properties and other properties are varied. So mainly reactivity, optical properties, magnetisms, they are highly affecting by the reducing of the size. So in terms of reactivity, as particle gets smaller, they tend to react differently with their environment than larger particles. So what happened actually? So suppose in a larger size, some particles they are highly reactive, but the same material, the same particle, you can say at a lower size, they are inert. They are basically inert. And in terms of optical properties, so smaller particles can have different optical properties. Their color will change because different size of particle reflect and absorb light differently. So here you can see a gold nanoparticles. So as you reducing the size from a micron to nano, it will change color from purple to red color. So this is only because of the absorbance of light differently actually. And in terms of magnetism, smaller particles can have different magnetic properties than larger size. Suppose, for example, you can say iron nanoparticles, they are showing, the fluctuate magnetism, fluctuate magnetic properties rather than its bulk size. Basically bulk size are showing, stable magnetic properties. So that's why as we decrease the size from higher to lower, magnetic properties will change. So this is about why nanoparticles are different from larger particles. What is the reason behind that? They are showing in different activities. So here the two principal factors cause the properties of nanomaterials to differ significantly from other materials. That is, the one is increased relative surface area and quantum effects. So these are the two main factors that are affecting nanoparticles at large. Then these factors can change or enhance properties as reactivity, strength, and electrical characteristics of that particular material. So now, as a particle decrease in size, a greater portion of atoms are found at the surface compared to those inside. So if you see this particular scheme, you can see over here. So this is the larger particle. So and this one is the smallest particle. So this you can say a yellow portion is related to surface atoms. These are on the surface, and this black portion is related to inner atoms. So as the particle size decrease, so you can see the maximum atoms are, or you can say very limited maximum atoms are on the surface instead of inside the matrix. So due to that one, you can say surface energy is very high. Okay, so this is the main reason. As the surface, as the particle size decrease from higher to lower, then quantum effects directly affecting on the surface energy of that particular material. Okay, and here you can see in terms of surface area. So at a higher size you will get lower surface area, and at a lower size, at nanometer size, you will get higher surface area. So this you can say at a lower size, maximum particles can occupy the maximum portion of that particular matrix. So that's why nanoparticles cover the maximum surface area when you incorporate in any polymer matrix like polyethylene, polypropylene. So it is a interdependent, you can say, technology. So the principal one means that you can say that surface area, quantum effects, and size, these are interdependent and interconnected also. So so you can say that when we are reducing the size, the surface area and surface, you can say, quantum effects is largely affecting. And you can say, and due to that one, these nanoparticles shows different properties in terms of reactivity, strength, and electrical characteristics. So these are the examples of some ancient nanomaterials. So you can see that Liker glass cup containing gold, silver, alloyed nanoparticles. So it shows, you can say, green in color when light passes through in focus light actually, and it shows reddish pink in color when diffuse light, under diffuse light. And this is the motherable stained glasses with nano pigments. So these are the gold pigments, or you can see gold pigments showing different colors at different size. Okay. Now some examples of ancient Ayurvedic nanomaterials, that is bhasmas. So bhasmas are basically Ayurvedic medical powders prepared by the process of calcination of metals or minerals. So basically, calcination means nothing but the purification of that particular metals and gems and minerals. So bhasmas mostly contain various metal like gold, silver, copper, zinc, having end products like swarna bhasma, rajat bhasma, tamra bhasma, and yasad bhasma respectively. So these are the different types of bhasmas you can see over here. So nanoparticles preparation method. So there are basically two types of methods are basically implemented for the preparation of nanoparticles. One is top down approach, that is microfabrication, and another is bottom up, or you can say self assembly. So in terms of top down approach, nanoparticles are prepared by breaking down of bulk solids into nano size. So basically, it is a mechanical process, and ball milling is the best example for top-down approach. So bulk materials are converted into powder, then powder are converted into micro nanoparticles. In terms of bottom-up approach, atoms, you can say nanoparticles are synthesized by assembling the atoms molecules together. So it is a chemical process, and basically micro nano emulsion, CVD, with different types of nanomaterials by chemical vapor deposition process is the best example of bottom-up approach, where atoms are converted into clusters then converted into micro or nanoparticles. So what are the polymer nanoparticles? So basically, polymer nanoparticles are tiny particles, typically in the range of 1 to 1000 nanometer in size, made from polymers or copolymers. The ultrafine particles have size between 1 and 100 nanometer, and fine particles are in between 100 to 1000 nanometer. So the best examples are mycelial capsules, then spheroids, colloids, then dendrimers, core cells, some nanoparticle incorporated polymer matrix and fibers, These are the examples of some polymeric nanoparticles. So the micelle is the first pharmaceutical polymer, produced in between 1960 and 1970. So this is about the polystyrene nanoparticles synthesized by a microemulsion process. Here you can see. So synthesis of polymeric and hybrid nanoparticles. How we can synthesize different types of polymeric and they are hybrid nanoparticles. So by dispersion, mini-emulsion, microemulsion, nanoemulsion, then by in situ polymerization process, microwave assisted emulsion polymerization process, sonic-chemical process, sol-gel process, and so these are the processes, synthesis processes. By that process, you can synthesize different type of polymeric and hybrid nanoparticles. And so I have synthesized different types of nanoparticles mainly by microemulsion and sonochemical processes. So these are the different types of polymeric as well as you can say hybrid nanoparticles I have synthesized and incorporated in different polymers like LLDP, LDP, LLDPA, LPP, then HIPS, SBR. Okay, so this is nothing but the blending process, blending and you can say a mixing of solute structure in nanostructure in polymeric materials. So overview of various heterophase polymerization techniques. So here you can see different polymerization techniques from precipitation to microemulsion process, and by that process you can synthesize particles from millimeter range to nanometer range. And microemulsion process is the best process to get you can say particles uniform particle size distribution in between 100 to 10 to 100 nanometer. So this is the well accepted and you can say most popular process to synthesize polymeric nanoparticles, that is microemulsion process. So there are different types of microemulsion process, that is microemulsion, seeded microemulsion, modified microemulsion process. I have patented one newly you can say accepted method, that is atomized microemulsion process. I will discuss later. So why microemulsion? Why we are using microemulsion? So the advantages of microemulsion process are basically you can say so the control of the input variables is easily possible. First, second is greater control on particle size. Then the end properties are better than other variable methods such as mini emulsion, solution, bulk, and suspension. Then precise control on process parameters. So these are the actual say you can say advantages of microemulsion process. And what are the features of microemulsion process? It has large internal interfacial area, optical transparency. So you can see over here that very transparent or translucent form of polystyrene nanoparticles could be you can synthesized with the help of microemulsion process, and a small domain length scale and greater variety of structures. So we can get very you can say a polydispersity index is very high whenever we are using microemulsion process. And also you can get different types of structures depending on the use of different types of surfactant. Okay, so we'll get different types of structure of polymeric nanomaterials and other inorganic nanomaterials also. So this is about the modified microemulsion synthesis process. Here I have synthesized polystyrene as well as polymethyl methacrylate nanoparticles with the help of modified microemulsion process, where sodium dodecyl sulfite used as a surfactant, and you can say ammonium persulfate as an initiator over here. This A1, A2 is related to styrene nanoparticles, and B1, B2 is related to you can say polymethyl methacrylate nanoparticles. And for A1 we'll get here you get 47 nanometers size nanomaterials, where in A2 58, and for methyl methacrylate that is 35 and 50. Here you can see A1, A2 and B1 and B2. So as the particle size decrease, transparency is, you can say, increase over here. You can say clearly over here that transparency is increase with decreasing of the particle size. So this is about the differential scanning calorimeter analysis of polystyrene and polymethyl methacrylate. So this here you can see basically the melting temperature of pure sodium dodecyl sulfate at 60-degree temperature and 170-degree temperature. These are the two melting peaks basically present in pure SDS, and this is the glass transition temperature of commercial PS, that is 94. For bulk PS is 93, and for pure polystyrene nanoparticles is 108, where the second scanning shows 105. So if you compare the glass transition temperature with bulk and commercial PS with nanoparticles, then there is a hike of glass transition temperature. So what is the reason behind that? The reason is same, that as the particle size decrease, surface energy is increased. So due to that surface energy, higher surface energy at a transition temperature, they are instead of you can say releasing heat, they are absorbing instead of absorbing heat, they are releasing heat. That's why the transition temperature is automatically increased from 94 or 93 to 108. Okay, the same thing is happening in terms of polymethyl methacrylate nanoparticles. For bulk polymethyl methacrylate it is 107, whereas for polymethyl methacrylate nanoparticles it is 128. So this is the another process, atomized microemulsion process. This is my patented polymerization process. Actually, I patented in 2013. So by that atomized microemulsion process, I've synthesized polystyrene nanoparticles, SAN, polystyrene nanoparticles, then polymethyl methacrylate, polyacrylonitrile nanoparticles, and also the copolymer of polystyrene and polyacrylonitrile nanoparticles, that is polystyrene acrylonitrile as a copolymer nanoparticle. So here you can see that highly crystalline nanostructure, hexagonal nanostructure of polystyrene we have achieved with the help of atomized microemulsion process, where this is the you can say polyacrylonitrile nanoparticles with the help of APS, means ammonium persulfate, as an initiator, and this one is with the help of benzoyl peroxide as initiator. So as we changing the initiator from APS to BPO, then you can see the morphology is changed from crystalline to amorphous, means from crumb-like structure to spherical-like structure. And here is the mixing of crumb-like and spherical structure is present when we are synthesizing copolymer of styrene and polyacrylonitrile as a copolymer nanoparticles. Now, this is the new type of nanoparticle, that is inorganic or organic hybrid nanocomposites or nanoparticles. So basically, encapsulated means core cell nanoparticles consist of hard core and a soft shell, or vice versa. Okay. So hard phase consists of inorganic materials and soft phase consists of organic materials. Here you can see this hard portion, it is the core as inorganic particles, and soft shell as a polymeric chain chemically grafted on that particular solid surface. So these are the applications of core cell nanoparticles, from paints to electronics. So my actual field is here, it is in plastics and rubber. So again, advanced atomized microemulsion synthesis of calcium carbonate polystyrene nanoparticles. So this is the you can say a reactor where I've synthesized calcium carbonate polystyrene nanoparticles. So these are the transmission electron microscope of image of core cell structure of calcium carbonate and polystyrene nanoparticles. So here you can see the 52% grafted calcium carbonate for A, with 36% free nanocalcium carbonate and 12% free polystyrene nanoparticles. Here you can get. So in microemulsion process, basically grafting of you can say polymeric cell on solid particles is very important. So the depending on, you can say, addition of monomer or converting of monomer from polymer, that is very important in terms of grafting of polymeric cell on the surface of solid nanoparticles. So these are some examples of hybrid nanostructures I have already synthesized in my laboratory. That is nano calcium silicate, acrylonitrile butadiene, then nano calcium carbonate, ANB, acrylonitrile butadiene, nano calcium silicate, SAN, nano calcium carbonate, SAN, then nano calcium carbonate styrene butadiene. So this is the nano calcium carbonate polymethyl methacrylate and nanostructure I have synthesized in my lab. So this is, here you can see the nano calcium carbonate with a polystyrene layer. Here you can see the average 20 nanometer of that layer grafted on the surface of calcium carbonate nanoparticles. So basically, it's a chemical process. So polymeric layer is chemically grafted on the surface of nano calcium carbonate through through, you can say, silane coupling agent, that is triethyl vinyl silane. Actually, so it is the process, a chemical process where nano polystyrene chains, small chains, they are anchored on the surface. Here you can see over here. So now, nano blends and nano composites. What happened actually? Whatever the nanoparticles I have synthesized, like polystyrene, polymethyl methacrylate, then all these nanoparticles I have incorporated in different polymeric matrix. That is polypropylene, LLDP, and PS using Bravender plastic order. And from 0.1% to 0.25, sorry, from 0.1% to 1% of loading of nanoparticles, you can say, we have studied in different field. So the process temperature was set at 190 degrees centigrade at 60 rpm rotor speed for 10 minutes. The sample volume for each blending was kept constant, means 90% of volume capacity of the cavity, that is to study the variation in torque and melt viscosity of different percentage weight of core cell nanoparticles. So here, this is the plastograph results of pristine polypropylene and 0.1%, 0.25%, and 0.5% of NPS nano polystyrene loading actually. So here you can see the rheological study of you can say nano polystyrene incorporated polypropylene. So at 0.28 percentage of loading, you can see the melt viscosity is very less, very only 47. So what is the reason behind that? The reason is nothing but that polymeric nanoparticles, they are basically acting as a lubricant, and they are acting, or also they are providing, they are acting as a media to to enter in between that chain segments of two polymeric chains in the polymeric matrix. That's why they are one side, they are you can say holding the polymeric chains, and as well as you can say they are increase the flexibility of that particular matrix, and that's why the melt viscosity of that particular media is decreased. So this is about the DSC and TGS studies results of the same you can say blends. So here at actually it would be this red portion would be in P2. So here you can see in case of P2 it is shows the highest properties. Okay, the thermal stability is almost 473. So it has shown only with the 0.2% of loading, nanoparticle loading, the thermal stability is highest as 473. That is the offset temperature, and onset temperature is 382. So and other you can say properties like cold crystallization, melt crystallization, also you can say increased for that only 0.28 percentage of loading. So mechanical properties. So in terms of conventional, theory, what will happen? Basically, when the tensile strength increase, elongation at break is automatically decreased. This is a practical phenomena in terms of polymeric materials. It is the nature of polymeric materials. But whenever we are adding nanoparticles or polymeric nanoparticles in any, you can say, a polymeric matrix that may be of polypropylene or polystyrene or polyethylene. What happened as we incorporate nanoparticles from 0.1% to 0.1% to 0.5%, so it will continuously increasing. So from 30 to 33, then 40, up to 0.25 percentage of loading, it will show the highest property, you can say. So that is the 40 megapascal, and again it is decreasing up to 34 megapascal. So, but in terms of elongation and break, it shows the same, you can say, nature. So from you can say elongation as we incorporate polymeric nanoparticles at 0.2 percentage loading, elongation is also high. Modulus is also high in terms of loading of the nanoparticles at 0.28 percentage of loading. So you can say that when this is the actually a magic of addition of nanoparticles in polymeric matrix, basically different polymeric matrix. So with a very minute addition of nanoparticles, the entire property of that matrix is changed. So here you can see what happened actually after addition of nanoparticles. They are interlayer slippage. You can see over here. There is a means polymeric nanoparticles. They are acting as a lubricant as well as they are providing strength in that particular matrix by holding large molecular chains of the polymeric matrix. So that's why tensile strength as well as elongation and break both are increased. So this is about the when we are adding core cell structure or hybrid structure in polypropylene. Here you can see with 0.1 percentage of loading. Here is 1 percentage of loading. Here is also 1% in a high resolution. You can say. So this is the ungrafted calcium carbonate, and this is the grafted means polystyrene grafted calcium carbonate basically. So with only 0.1 percentage of loading, there is no you can say a particular change is not observed over here. But when we are increasing the percentage from 0.1 to 1, here is the clear difference you can observe. So basically for ungrafted calcium carbonate, you can see the particles are on the surface, but with grafted nanoparticles, you can see that maximum particles are integrated with the polymeric matrix. So means they are inside the matrix. They are uniformly dispersed. And this is the high resolution structure picture. Here you can see the aggregation of nanoparticles with the same 1% of loading for ungrafted calcium carbonate nanoparticles. But here you can see all nanoparticles are uniformly, you can say, dispersed in the polymeric matrix. Again, tensile strength as we incorporated this core cell nanostructure in polymeric matrix, then tensile strength is continuously increasing from 0 to you can say 5% of loading. And here is also same for elongation at breaks, is continuously increasing. This is about the calcium carbonate, means same core cell structure in high impact polystyrene. So here is with 0.1 to 5% of loading. Here you can see for ungrafted materials, ungrafted calcium carbonate nanoparticles. Here with 2% of loading, phase separation is observed. But here with 2% of grafted nanoparticles loading, there is no phase separation. But at 5% of loading, both are showing the same phase separation. Okay, so it is the unique study I have done during my, you can say, uh, studies. Here is also AFM studies. Here you can see for the same you can percentage of loading. As the percentage of loading increase from 0.1 to 5%, whiteness of that the white you can say color is increased. Why? So it is not. It is just you can say you can say related to you can say aggregated nanoparticles in the polymer matrix, whereas with a core cell structure loading you can see maximum dark color, means uniform dispersion of nanoparticles happened during mixing. So this is the main reason that we are incorporating core cell structure instead of ungrafted or you can say only silane modified nanoparticles in polymeric matrix. So now this is about the multi-layered inorganic organic hybrid nanostructure. So I have synthesized. So this is about the different. This is the combination of different materials in the same matrix. So the capsule portion is basically the nano calcium silicate, and then calcium carbonate is grafted on the surface of calcium silicate. Here you can see the calcium carbonate is grafted on the silicon structure, and that silicon you can say calcium silicate and calcium carbonate is double grafted with PLA. So it is the multi-layered you can say polymeric means hybrid
Hello.
nanostructures with
Hello.
calcium silicate.
Uh, Hello.
Yeah,
Sorry for the interruption, sir. I think you have 5 minutes left. So can you please wind up within the 5 minutes?
yeah.
Yeah.
So this is layer double hydroxide. You know, I have synthesized by biosurfactant with the help of biosurfactant as a surfactant and amnolipid, and the same layer double hydroxides are used for synthesis of polyacrylonitrile base activated carbon. So we have synthesized by you can say by uh, by sonic chemical process. Actually, here you can see activated carbons are inside the layers. So this is reusable water filter columns, basically used for filtration of water, potable water or drinking water. Okay. This is one-dimensional sub 10 nanometer nanofabrication of ultra hydrophobic AGTI to nanowires. So nanowires are used, and we have used for self-cleaning textiles materials. Basically, here you can see the you can say water droplets. They are not they are stable on the surface of cotton fabrics actually with 10 second of interval. So, what are the future prospect of nanotechnology in India and as well as the world? So, global prospect. So, basically, a global future prospect of nanotechnology includes in healthcare and medicine, where targeted and sustained drug delivery systems are basically developed. Then, creation of advanced diagnostic tools, wearable health sensors, and even nanorobots for surgery is the we can say great future for nanotechnology. Then in terms of electronics and computing, smaller, faster, and more energy efficient transistors and chips. Then potential rays of quantum dots and nano memory for super fast data storage. Then in energy sector, that is for solar cell energy storage innovations like nano enhanced batteries and capacitors. For environment, nanofilters, cell cleaning materials and pollution control technologies are the great prospect. In agriculture, nano fertilizers and pesticides for increased crop yield with reduced chemical use. Nanosensors for soil and plant health monitoring. Then defense and security, that is development of lightweight armor, slate materials and chemical biological detectors at the nanoscale. In terms of Indian prospects, India has strong ambitions and growing initiatives in nanotechnology. So some important points is related to, you can say, government support. That is, in 2007, Government of India launched Nano Mission under the flagship of Department of Science and Technology. Then heavy investment in research infrastructure, established so many research center of excellences for nanotechnology in IITs and NITs. Then healthcare innovations. Indian research institutes are developed cost-effective nano-based diagnostics important for rural health. Then work on affordable nanomedicines to combat disease like tuberculosis, malaria, and cancer. Then in agriculture field, so research is going on in nanofertilizers to reduce reliance on traditional chemicals and boost sustainable farming. Recently, IFCO launched the world first nano liquid urea fertilizer in June 2021, and thereafter a nano DAP fertilizers was introduced in April 2023. In terms of energy and environment, development of low cost nano-based water purifiers, basically Tata's Swachh purifier used nanotechnology, then focus on solar energy innovations through nanomaterials, startups and industry, growth in nanotech startups in biotechnology, energy, electronics and materials. Sectors like pharma, textiles and food are starting to adopt nanotechnology for product innovations. What are the challenges for the future? So these are the few challenges like regulatory framework. So need for clear rules and guidelines on nanotech use, especially in healthcare and environment. Safety concerns, long-term effects on nanoparticles on health and nature are still under study. Then find funding and collaboration, more you can say international collaborations and private sector involvement are required for the development of nanotechnology in India. The skilled workforce, the building expertise in nanotechnology at the university and industry level remains critical. So in final conclusion, globally and in India, nanotechnology will be a game changer across industries. It holds the promise to address critical challenges from sustainable energy and clean water to advanced healthcare by responsible development and deployment are essential to minimize benefits. So thank you for your patience. So our next topic is on plastic sustainability and recycling at Crossroads. Where do we go from here? So on 8th May at 4 to 5 p.m. by Samir Joshi, Chairman of IPR Mumbai. Thank you.
Yeah.
Thank you very much. So if you have
Thank
any
you, Dr.
questions.
Chatterjee, for the highly informative session on transformative role of nanotechnology in modern science. So floor is open for the questions now. So participants, if you have any questions, you can drop them out in the chat box. So I can see here 2-3 questions are there. So we will try to take as many as possible. Uh, Sir, can you please answer the first question?
So where is the question actually? I have to check
Yes,
now.
sir. Yes, sir. I can read it. I'll read. What is the role of
Yeah,
nanotechnology?
what is the role of nanotechnology in existing technologies or create new ones? So I have already discussed in this particular presentation that nanotechnology is change the total horizon in technological and scientific field. So right from medicine means right from medical technologies to self cleaning paints actually. So, and it has the great future in all sectors basically. I have already mentioned one topic, that is nanorobots. So nanorobots is the future technology. So this will change the scientific world by 180 degree shift, you can say. And another one is, can nanocomposites be blended with recycled polymers? Yes, obviously. It will be blended with recycled polymers and you will get higher properties. Higher properties. Okay. And last one is, how can we ensure uniform dispersion of nanoparticles with large quantities of polypropylene? Is that from? Is that from? क्या है? Is that from?
It is manufacturer perspective, sir.
From manufacturing perspective, okay, how can
Yeah.
we ensure uniform dispersion of nanoparticles? See, the main problem is with nanoparticles is they are very sticky. Yeah. They are not properly or uniformly dispersed in the polymeric matrix during processing. So it is very important that before incorporating these nanoparticles, proper surface modification is very important. Okay. Conventionally, malic acid, silane coupling agents they are using or to reducing the you can say aggregation of nanoparticles during processing. But this is not the highest one. So I have already mentioned over here, core cell nanostructure is the best way to eliminate aggregation of nanoparticles during processing. So that polymeric layer on the surface of inorganic particles, they are helping to disperse nanoparticles in the polymeric matrix at a large. Okay. And the main important thing is that basically whatever the you can say inorganic materials or fillers are using to enhance the properties of polymeric nanocomposite, they are basically hydrophilic in nature, water loving, and polymer is basically hydrophobic in nature. So it is the mismatch. So first we have to change the surface morphology from inorganic to organic. So that's why grafting of polymeric materials on the surface of calcium carbonate or any failure as a cell, it is very important. So it will, one side it will you can say match the hydrophobicity with the hydrophobicity, and also help to disperse all these nanoparticles in the polymeric matrix uniformly. That is the main reason. And the last one, और क्या है? How can we ensure uniform dispersion? Then you have done with RK on PMMA through looking at benefit any high engineering polymer for auto application. Automobile. I could not understand these questions actually. Next one is, what are the future of nanotechnology in plastic industries? So future is very, very, you can say, it has a very large future, you can say, very large future and very prospective future. So sky is the limit. We don't know after maybe 30 years and 40 years later what will be the technological development in nanotechnology, because today we are working in between 10 to 100 nanometers, but now research is already started in below 1 nanometer, that is in quantum dots. Okay, it means it's pico technology, less than 1 nanometer. So really you don't know what will be the future, but you can say we have a great future, very advanced future with the help of nanotechnology. Or you can say the future today you are in for example, for basically in construction field. We are using steel as a you can say composite material basically. Now that steel would be replaced by a nano composite in future, because now we have graphene, single atom layer of graphene, then carbon nanotubes. So carbon nanotube is 10 times stronger than steel, and graphene seed is 30 times stronger than steel. The only problem is they are very lightweight, and the mixing of these nanomaterials in polymeric matrix is very difficult. And research is going on. I mean, maximum research, intensive research is going on how to dispose this carbon nanotube and graphene in polymeric matrix.
So I extend my heartfelt thanks to Dr. Anirudh Chatterjee for informative session. And I also would like to thank Dr. Gupta for addressing PIU. So thank you to all participants for your active engagement. So this is just a quick reminder to all. Our next session of Parivartan will be held on 8th May 2025. So we would look forward to your presence. So thank you everyone again. Have a wonderful evening. Thank you.
Thank you.